introduction, and today we have our second talk. The speaker is going to be Carlos Simpson, a man who needs no introduction, and he's going to talk about points near infinity in modular spaces of local systems.
So thank you very much. So I'd like to thank the organizers for organizing this great conference and in this really beautiful and very interesting setting. So I'd like to talk about some work which we've been doing. This is going to be a sort of a review in some way of work that we've been doing with Ludmil, with Alex Noel and Pana Pandit, and also Fabian Hayden made some important contributions in motivation for what we're doing, and also some Andy Neitzke helped us with some important comments. Okay, so let me just start by talking about very briefly about the moduli spaces of local systems. So we have, let's just for today, let's just have X is going to be a smooth projective algebraic curve. One could, I suppose, try to understand what's happening with this whole theory in higher dimensions, but we haven't started to look at that yet. So we have the moduli space, which is usually called the character variety, which is the space of representations of the fundamental group of X into, for example, SLR, SLRC that means, and divide by the action, the conjugation action. And this is a GIC quotient in the sense that it's not really a quotient. The points of this space are S equivalence classes of representations. Two representations are S equivalent if they have the same semi-simplification in the Jordan-Holder series. And this is an affine variety. Procesi's theorem tells us, it gives us in fact generators for the coordinate ring, which are the functions trace of a matrix applied on a group element. So we have a nice coordinate ring. This guy is an affine variety. You can just sort of write down equations, the generators for pi1 of x and its single relation, give you equations for this variety, and then the GIT quotient is also the space is spec of the ring of invariant functions under this action. So the quotient is an affine variety. Now, this is a classical thing which you can look at for any group. But in the case of a smooth projective curve, we also have two other spaces. One is the space introduced by Hitchin, the space of semi-stable Higgs bundles of degree 0. So Higgs bundle is a vector bundle plus a Higgs field. We'll see that on the next slide. Again, modulo the same type of S equivalence relation. And then the M Durand moduli space, it's the moduli space of vector bundles with an integrable algebraic connection over X. Again, modulo S equivalence. I guess I didn't write down here I said degree 0, but in fact, for the group SLR, that means that we should have objects with a trivialization of the determinant. And now this is sort of a remarkable collection of spaces because these three spaces are all algebraic varieties, but they have a quite different nature. And nonetheless, we have a homeomorphism of varieties between Hitchin's moduli space and the other two. And the Riemann-Hilbert correspondence gives us an analytic isomorphism of complex varieties between the character variety and the Durand moduli space. This analytic isomorphism is not an algebraic isomorphism, and this is not even complex analytic. For those of you who know something about it, this complex structure and the complex structure here form a part of the triple of complex structures that gives you a quaternionic structure. It gives you a hyperkähler structure of the moduli space. So this is one of the complex structures, and these guys are the other one. Now, what I'd like to talk about today is really the compactifications of these varieties. Remember that the Betti moduli space is an affine variety, so if it's not just a finite collection of points, then it's non-compact. So it has to have some points at infinity. There's something called, that the topologists have introduced, called the Morgan-Shalin compactification, which, however, is not an algebraic variety, and roughly speaking, it's putting some kind of valuations at points at infinity. On the other hand, these two varieties are somewhat nicer for the problem of compactification. They have compactifications that are algebraic varieties. I'm not going to write the formula for the compactification, it's not too hard. But I'd just like to say the compactification is the moduli space plus a divisor, which I'll denote by K. And the divisor is the same in both cases. And we can write it down like this. It's obtained by taking the Hitchin moduli space, subtract the nilpotent cone. So this means all the points such that phi is a nilpotent operation. And we'll also see in the next map, it's also the nilpotent cone is the inverse image of 0 under the Hitchin vibration. So we sort of remove something and then divide by C star. This is very much like what you do when you define projective space, right? You take the affine space minus the origin and then divide by C star. So this divisor, this guy is the same guy that goes at infinity in both of these spaces, which is sort of suggesting something which is true, which is that these spaces are closely related in the sense that there's a deformation from one to the other. But their structure as algebraic varieties is nonetheless pretty different. So now we have what's called the Hitchin vibration. So this is a map. Well, I'll say what that is again in a minute. This is a map from the Hitchin moduli space to an affine space. And well, what we saw here is that we have an action of C star on this space. If we go back to here, I guess. The action of C star is just multiplication of the phi of the Higgs field. Then that action, this map is equivariant for an action of C star. It's not actually the trivial, it's not the usual action of C star on the affine space. There's a weight. Different coordinates are acted upon by different, with different weights. But just think of that as it's basically the same as the usual action. And so the base, we can compactify that to a projective space of the same dimension. And the divisor at infinity it's a similar looking thing. It's just the affine space minus the origin modulo C star. This procedure, as I said, this is about the same thing as what's happening for the compactification of MH itself. Basically, anytime you have a variety and a C star action, if the C star action has the property that when you go towards 0, it lands you in a compact subset, that's the nilpotent cone, then if we sort of take away that compact subset in the middle and take the quotient of the rest by the C star action, that'll provide a divisor at infinity and you'll get a compactification. That's just the general. So now let's just view, there's this weight because the action of C star on AN is not the usual one. So it's a weighted projection space. And well, it's best to view this as a smooth Dilley-Mumford stack. And now when we make this projectivization, we get a map from the compactification to the projective space. Again, that's just pretty much because we use pretty much the same procedure to define these compactifications as we did to define that. So in particular, the divisor at infinity here maps to the n-1 dimensional weighted projective space that we put at infinity. Now, when we have a projective space, or for example, a weighted projective space, there's something called the Hopf vibration, which is a sphere, dimension 2n-1, mapping to Pn-1. And we can think of the sphere as being the quotient where we take the affine space minus the origin and divide by the action of r plus star. So instead of dividing by C star, we divide by positive real scalars. So that's going to be just the sphere. And it doesn't really matter that there's the weight or not. It's always going to be the sphere. If I'm not mistaken. And so we have a map like that. That's an S1 bundle. Now we can just pull back that S1 bundle by this map. So we get a Cartesian diagram here. We have an S1 bundle here. We just pull that. We make a fiber product. We get an S1 bundle, which we'll call K tilde, mapping to K. And again, it's the same thing. We take the Hitchin moduli space minus the nilpotent cone and divide by the positive real scalars rather than C star. Why am I doing all this is basically because when we go out to infinity, this is going to depend on the sector in the complex plane, the direction that we go out in the complex plane. If we sort of have a curve going out to infinity, that curve is a complex disk, for example. The behavior is going to depend on sectors in that disk, so we should sort of distinguish different sectors. Then we can define what you might call Borel-Serre type of compactifications of these spaces, where instead of adding the divisor k, let's just add, it means we sort of do a real blow up along this divisor. And instead of the divisor, we add the S1 bundle over the divisor. So again, we're just distinguishing directions as we go towards the divisor. So let's call that a Borel-Serre compactification. So we just add this k tilde instead of k. And then we can even go from there. We can then squish if we like. Because remember, we have a map from k tilde to the sphere. So we could just take the quotient as a topological space on the k tilde. So then, contracting this k tilde to Sn minus 2n minus 1, we could get a compactification where you just add the sphere at infinity. So these guys are no longer algebraic varieties. I mean, these guys are not algebraic varieties either. They're somewhat close to algebraic varieties. They're the real blow-up. These guys, we've sort of squished a bunch of things. So this procedure, we could actually even squish more. We could just add the Pn minus 1. And that would be, again, that would not be an algebraic variety, but it would be a little closer to an algebraic variety. That maybe one should think of as a Satake type compactification. So this is kind of a circle bundle over Satake compactification. Now let's, on the other hand, go back and recall that we had this Morgan-Challen compactification of the character variety. Let's call KMS as the boundary. And well, it's kind of hard to say what the points correspond to, and people have written a lot of stuff on that. Roughly speaking, they correspond to valuations on the coordinate ring of the affine variety, of the character variety. For the group SL2, these valuations correspond to actions of the fundamental group on R trees. So you can say sort of the Morgan-Challen boundary is equal to actions of the fundamental group on R trees in some way. And that's been extended recently by Parot, who has shown that for higher rank groups, for SL3, SL4, and so on, that the Morgan-Challen boundary points also correspond to actions of pi1 of x on Euclidean R building. This is kind of the thing that we're going to be looking at. Now, for the case of SL2, these compactifications have been studied quite a lot by low-dimensional topologists. So the literature is quite vast on that. One thing to know, which sort of makes a link between that literature and the stuff that we're looking at with the Hitch and moduli spaces, is that Daskalopoulos, Dostoglu, and Wentworth this was like in the beginning of like 1990 or something like that, 1991 maybe. They defined a map between the Morgan-Challen boundary and this S2n minus 1. And they show that their map is homomorphism. So we're interested in looking at something like this type of question. But we're interested in looking at that for groups bigger than SL2. But let me stick with SL2 for the moment. Let me just describe an example. So this, I think, is pretty much the simplest example where we're going to have a non-compact character variety. And I think it's an important example. It sort of shows you what happens, basically. So it's important to understand this example. So for this example, unfortunately, it's not really a curve. It's a Deligne-Mumford stack or an orbital. So x is P1. It's a root stack with P1, and we have 4 points. And then we add some denominators at those 4 points. We're going to look at representations of pi1 of this space. What that means, a representation of pi1 of this space into SL2 is going to be a representation of pi1 of P1 minus the 4 points, but such that the loops around the 4 points go to matrices of order n1, n2, n3, n4. So a matrix, a semi-simple matrix of order ni is going to be something of the form, for example, zeta I inverse, something conjugate to zeta I, excuse me, that shouldn't be an equal, that should be a conjugate. The representation is something where the value rho of gamma I should be conjugate to a matrix of this form, where zeta I is an nth root of unity. So let's fix that data. So we'll fix the ni's, we'll fix the zeta i's, we'll fix the conjugacy classes of these matrices. Then you can define a moduli space, which is all the representations such that the matrices are conjugate. And the nice thing about that is that it's a two-dimensional complex variety. So that's the smallest possible thing. Because of the fact that there was a hyperkähler structure, it means that the real dimension is divisible by 4, so the complex dimension is divisible by 2. So we're not going to be able to have a one-dimensional example. So this is the smallest kind of example we can find. There's actually a certain number of examples that are of this form. They correspond to what's known as the Penalove equations, and this is the Penalove 6 equation. I should say, there's some other examples where there's only 3 points, so there's no Penalove equation because the points can't move. There's not too many examples. Now, on the side of MH and M Duram, the compactifications are actually smooth orbifolds, if we assume that zeta is kind of generic. The compactifications are smooth orbifolds. And the divisor at infinity, well, it's basically the elliptic curve, except it's not the elliptic curve, it's the elliptic curve divided by the involution. So it's P1 with orbifold points of order 2 at these points. So it's the root stack. Now, if we look at the fibration, so S1, this is the S2n minus 1, which came from the base of Hitchin fibration. And so this is basically the Hitchin fibration at infinity. The fibers as we know that the fiber of the Hitchin fibration is in abelian variety. We have a 2-dimensional moduli space. The Hitchin base has dimension 1, so the fiber has dimension 1. The fiber has to be an elliptic curve. And in fact, in this case, it's the elliptic curve that's branched over these 4 points in P1. So the fiber is a torus, S1 across S1. And if you think about it, if you do the calculation a little bit, you see that when you go around this S1, going around this S1 corresponds to going around the point at infinity in the A1 of the Hitchin base. One can see that the action is actually the hyperelliptic involution on the elliptic curve. So this is not a trivial fibration. It's a fibration where when you go once around S1, that acts by -1 on the torus. And this K here is sort of the quotient of that action. Now on the other hand, so that was the Hitchin case. Remember, this divisor K is the same for the Hitchin and for the Duram case. On the other hand, let's look at the character variety. The character variety, this is a classic thing called the Klein cubic surface. This was studied in the 19th century. Not so easy to write down the equations, but so that was done in the 19th century. I actually learned about that, and there's a nice paper by Domingo Toledo and Bill Goldman discussing this thing. That's kind of where I learned about the existence of this thing. Or maybe I should say relearned or something. But so if you want to have a sort of a modern approach to this whole thing, look at this paper by Bill Goldman and Domingo Toledo. It's a cubic surface in P3, and the divisor at infinity is a triangle of P1s. Maybe I should stress this is an algebraic variety compactification. It's not the Morgan-Shalin compactification. In some way, the Morgan-Shalin compactification is a little bit like taking the limit of this guy if we start blowing up all these points a lot. Anyway, here we're just fixing a single algebraic compactification. This depends on a choice of generators of the fundamental group. We have to sort of choose some loops here, and then there's a break group action here. This compactification is not break group invariant, so we've made some choices to get this picture. Well, so if we take our cubic surface in P3, we have a plane which is tangent at 3 points, and the intersection is 3 copies of P1. So these are 3 of the lines in the cubic surface. And the character variety itself is the complement of these 3 lines. So that means that the neighborhood at infinity, so points near infinity, are points in this neighborhood that I've shaded in here. I'm sorry, that was supposed to be a brighter color of blue to sort of reflect the ocean here, but I guess when it goes to the projector, it sort of gets it into the and here was the beach, right? So our points near infinity are this tubular neighborhood of this triangle P1. So one can see that, in fact, it turns out that one can really identify just directly this puncture neighborhood at infinity, homotopically speaking, with the K tilde. and we have a map to S1, and the map to S1 is the one you see here, namely, we have a triangle P1, so that's a triangle, and we just map we just sort of contract our neighborhood of infinity to that triangle, but to consider it as a real triangle. So that means, so remember these are P1, so that means that the segment from here to here, it's actually a C star. The transverse thing is at S1, so the fiber over a point like that in our triangle, in our S1, is really going to be an S1 bundle over C star, so again an S1 cross S1. The fiber near a point, like near a normal crossing point, is just a puncture disk cross a puncture disk, so homotypically it's S1 cross S1. And you can just sort of follow that around all the way. You see that the fiber over all the points is basically S1 cross S1, and as you go around a little matrix calculation, there's a little, the matrix that goes from one point to the other is a little matrix, 2 by 2 matrix, such that its cube is equal to minus the identity. There's a little matrix with 1, minus 1, minus 0, minus 1, I think, or something like that, minus 1, 0, whose cube is equal to minus the identity. So you can just really identify, in this particular case, identify everything that's going on. So from this example, we make the following conjecture. So we just sort of generalize this example to everything we might say. What's going on here? Well, what's going on here is if we take a normal crossings compactification M Betty bar, which is an algebraic variety, then we take its dual complex. So the dual complex is the thing where you put a vertex for every component, you put an edge every time 2 components intersect, you put a 2 cell every time 3 components intersect, and so on. You got a simplicial complex. It's known by Danilov, Touillet, Stepanov, and a number of people. It's known that the homotopy type of this complex is independent of the choice of compactification. For Phil, the cohomology of this guy is the lowest piece of the weight filtration for the fixed top structure. So we have this space which is the dual complex of any compactification that's independent of the choice of compactification. So the conjecture is that should actually be a sphere. In this case, it was a circle. That should actually be a sphere. And the map from the Lincoln infinity of our moduli space of local systems to this sphere should conjecturally coincide with the map that we had before, K tilde mapping to S2n minus 1. So that's a conjecture. I wrote a paper not too long ago showing that it really is, this first part really true. It really is a sphere in the case of P1 minus n points and rank 2 things. That may actually possibly already have been known by the topologists. It's a little bit hard to go through the literature in the topology thing and see what is really known about this question. Anyway, so there's a little bit of evidence for this conjecture. And in fact, the result that we said of Daskalopoulos, Dostoglu, Wentworth actually provides us with even more. It actually gives an identification between the sphere and a different compactification, but the Morgan-Shalin compactification here. The identification is only happening over an open subset. And well, this is just an opinion, but it looks like you might say, okay, can we extend the Daskalopoulos, Dostoglu, Wentworth statement to be an actual homeomorphism directly between the two spaces? It looks like that might not be easy to do. Maybe maybe one can define one, but maybe not so naturally. It looks to me like probably what's going on is there's some sort of real blowing up and blowing down occurring here, which should sort of preserve the homotopy type, but there might be some more complicated looking geometry. And in fact, what we'll be seeing next is going to sort of show it. I'm not sure. I think that should be pretty much the same open set as they have. But we're going to see sort of a genericity condition on points in K, where in the generic case we can sort of describe pretty explicitly what the picture looks like. Along what are called the walls, it's less clear what's going on. And so there may be some birational type of stuff happening along these walls. Okay, so now I'd like to talk about the WKB problem. So the WKB problem is the problem of ordinary differential equations, which you get when you start trying to look more precisely at the correspondence between these spaces. So remember we have our, let me go back here. We have these correspondences between moduli spaces. This correspondence is given by the Riemann-Hilbert correspondence. What does that really mean? That means that here we have a space of vector bundles with integral connection, and to go over here we should solve an ODE to get the monotomy representation of the integrable connection. It means we're solving a system of ordinary differential equations to go from here to here. So if we want to understand what that geometrically what that looks like, that means we need to know, sort of at least in the large, what the solution of the system of differential equations is going to be doing. That's called the WKB problem. So what we're going to be doing now is we're going to sort of restrict ourselves to a more specific geometrical situation. So we'd like to look at sort of families of points in either MH or M Durham, which go out towards the point at infinity in the divisor K. And as I said, that it's going to depend on the direction. So it's a point of K tilde. So remember, K tilde is the space of Higgs bundles with a non-nilpotent Higgs field phi. Again, we're about to see what that really is in just a minute. And it's up to positive real scaling of phi. So we can really think of a point, our point at infinity K, kappa, as corresponding to a Higgs bundle, except we just say that if we rescaled phi by a positive real number, then that would sort of correspond to changing a normal coordinate direction near the divisor at infinity. Now what's a Higgs field? Here's the thing I promised before. The Higgs field is just a map, a linear map of vector bundles from, locally free sheaves, from our bundle E to E tensor omega 1x. Okay, so it's like a connection. A connection is going to be the same type of map, but a connection is going to be a map which satisfies the Leibniz formula. So a Higgs field, one way of thinking of Higgs field is just the thing that you would use to perturb a connection. So if we take a connection nabla 0, then we can add a Higgs field, and we get a new connection, nabla t. So let's add t times our Higgs field phi. Well, I wrote nabla 0 is some d plus m. On an open set where E was trivial, then we have the trivial connection, and a given connection is going to be the trivial connection plus m, which is again the same type of thing. Anyway, we just start with a connection nabla 0, and then let's look at a family of connections, nabla t, where we add t times some Higgs field. And the idea is that t is getting big. So we're going to have a family of connections where some coefficients of the matrices are getting big. Okay? T is going to infinity. So for any point t, let's let the transport from P to Q as a function of t be the map from the fiber of E at P to the fiber of E at Q. So the transport matrix along a given path, I didn't include the path in the notation. Soon we'll be going to the universal covering, right? So it's the transport from P to Q. So that means we solve the differential of the ODE given by this connection. And we solve for functions such that nabla 0 plus t times phi times the vector v should be equal to 0. And then we take the solution going from the path from the point P to the point Q, and this gives us a transport function. So we're interested in understanding the rate of growth of this function as a function of t. This is classically called singular perturbation theory. So it turns out it's going to depend on a real ray in the complex plane. So it's going to depend on which direction t goes to infinity. That's why we did this k tilde thing. So let's look at t. Of course, we can adjust the real rate just by multiplying phi by e to the I theta to change the angle. So let's just assume that t is a positive real number. Now we have a similar problem for the Higgs bundle moduli space itself, because of course we can always take a Higgs field and perturb it by adding another Higgs field. But in fact, we can even just take the Higgs field itself. So this is a somewhat simplified. This is not the most general possible statement you could make, but a simplified version of the problem you could do here. Let's just consider the Higgs bundle E with t times phi as Higgs field. Then we solve Hitchin's equations. We let dt be the associated flat connection. And again, we have a transport for this flat connection. So in this case, we're not just solving a system of ODEs, we're solving a system of PDEs to get the solution of Hitchin's equations, to get the connection, and then we solve the ODEs to get the transport of that connection. So that's what we would call the Hitchin WKB. And in this case, we also have something additional, which is that the harmonic metric from the solution here actually depends on t. So this gives us a way we can measure the size in a way which is kind of adapted to this setting. Now we would like to define an exponent which is going to measure the exponential growth of this guy. Well, first of all, I should say, if you think about sort of your basic course in differential equations, the size of the solution of the differential equation is going to be exponential in the size of the coefficients, okay, as a general matter. So the size of this t pq is going to be some exponential of t. And this exponent, it just means let's look at the best possible exponent bound. So we'd like to take the limit of 1 over t times the log of the size of this matrix. That limit may or may not exist. So one thing to do would be to define a lim sup. That would really be the best possible exponent. Another thing to do, which actually turns out this is Perot's theory, which is we should pick an ultrafilter. An ultrafilter means just a point at infinity in the Stone-Check compactification. And then we can take the limit. Then these guys are bounded numbers depending on t by the basic ODE bound. So we can define something called the exponent depending on the ultrafilter. And we can also define the vector exponent, which I don't want to give a precise definition, but in the SL3 case, the vector exponent can be obtained from the exponent going from P to Q. The vector exponent has 3 components. The top component is the exponent for P to Q. The bottom component is the negative of the exponent from Q to P. And the middle component is determined by the fact that it's in SL3, so the sum of those guys should be 0. Now, our WKB problem is depending on this Higgs field, phi, right? I'm sorry, either here or here. The fact that the term that we perturbed to add. Okay. Now this Higgs field has what's called a spectral curve. So I didn't put a slide about spectral curves here. The spectral curve, it just means at each point of the Riemann surface x, let's look at the eigenvalues of phi. Phi considered as an endomorphism of the bundle. It's a twisted endomorphism. It's an endomorphism with coefficients in the canonical bundle. So the eigenvalues are sections of kx also, or sections of omega 1x. So they're really eigen one form. And let's just note by phi star the collection of r different one forms. So these are all defined up to permutations. Now, Perot's theorem is that there's going to be a harmonic map to a building. Depending on the building depends on the ultrafilter omega. That's kind of one of the main ingredients that Perot included here. There's going to exist a harmonic map such that the exponent is what's called the Finsler distance. In the next slide, I'll be talking about Finsler distance. It's what's called the Finsler distance in the building. Maybe I should say that this is an Euclidean R building, such that our exponent is the distance from h of p to h of q. And a similar version of this property is that the vector exponent is the vector distance from h of p to h of q in the building. Now our own little contribution here was that in the case of the WKB problem, of the Riemann-Hilbert WKB problem, we showed that the differential of this map is actually the real part of this phi. Perot was considering, in fact, it wasn't really considering a variety, it was considering actions of a group on a building and looking at sequences of points in the character variety, and said, okay, there's going to be a limiting action of the group on a building obtained by taking an ultrafilter limit. We just kind of did a groupoid version of that, where we had all the different points of x all together, and then differentiating using the classical WKB theory from like 1920, just the classical very local WKB approximation, allows you to differentiate this map and show that the differential is given by the spectral curve. And then Takuro Mochizuki, subsequent to a recent paper that you might know of by Matseo, Swoboda, Weiss, and Witt, Takuro Mochizuki proved the same statement for the Hidden WKB problem. In our paper, we had sort of raised that as a question, but didn't know how to prove it. So now that's also known for both WKB problems. So now this theorem gives us the following motivation. Can we calculate the distances in the building? Right, we have this map to the building. We know that the exponent is equal to the distance from one point to the other, and we know that the derivative of the map to the building is given by our one form. Okay? So can we sort of integrate this derivative that we know of the map to the building, sort of see what the long-range distances between points are to calculate the exponents? Or you might say the goal here is to calculate the exponent from one point to another. That amounts to saying, just as a very first-order approximation, what's the size of the solution of this ODE as a function of t? So we take a system of ODEs with a large parameter in it. We'd like to say, how big is the solution? So the question is, can we use the fact that we know the derivative to actually calculate the distances? Well, so this would provide us with many things if we are able to do so. So we should theoretically be able to say more about the Morgan-Shalen boundary points, because the Morgan-Shalen boundary points are sort of given by these they're given by these exponents considered as a length function on the grooves. We might be able to generalize, we don't currently know how to do this, but we might be able to generalize their result. It would give, among other things, we would get a calculation of this problem for a system of ODEs. And in fact, our actual motivation was for mirror symmetry. So we're hoping to be able to use this theory to generalize the Bridgeland-Smith construction of stability conditions on derived category. So now I'd like to just a little bit more quickly run through what we come up with. So we've only been able to really say something from now on for the group SL3. The point about the group SL3 is that our Riemann surface X has dimension 2, and the building for SL3 also has real dimension 2. So there's going to be a similarity of dimension between the Riemann surface and the building that we're mapping into. For SL4, SL5, and so on, the building is going to be bigger than the group. And there we don't really know how to talk about points in the building. So we're going to try to, in the SL3 case, we're going to try to construct points of the building. We don't know what the building is. The building a priori in Perot's theory is some gigantic thing obtained by the ultrafilter and some Gromov compactness argument and so on. So we're trying to sort of construct what's the image of our map from X into the building is going to look like in an a priori way using the differential. So we're restricting to SL3. So I'm just saying this is a very major restriction. And it's a major question what one might be able to do, even assuming we can understand what's happening here, which is not completely finished. But assuming we can understand what's happening here, then it's a major question to understand what would happen for higher rank groups. It's not just a small generalization. Okay, so let's take the universal cover, and then we take our, I'm sorry about this, I put tildes in because X was, at the start, X was a compact Riemann surface. Now we want X to be our sort of open, universal, simply connected Riemann surface. The tildes are going to sort of semi-go away in a minute, unfortunately. We have our spectral curve. This is the set of eigenforms of the Higgs field, considered as a curve in the cotangent model. It projects to X, and we have ramification points. So let's consider the branch locus. Away from the branch locus, the inverse image consists of 3 points Z1, Z2, Z3, and the images in the cotangent bundles are exactly these eigen-1 forms of the Higgs field. So these are the forms you get on the diagonal when you diagonalize phi, basically. Well, what's going on here is we're in the SL3 case, so the sum of these three guys is 0. So it turns out that we will actually be interested in the real parts of these differential forms. So these are real differential forms on our Riemann surface. Let's put phi ij, phi minus phi j. And we'll talk about a foliation line, which is going to be a real curve on X on which one of these real part of phi j vanishes. So in the SL3 case, there's 3 of them. There's 1, 2, 2, 3, and 1, 3. And they're negatives, but the negatives define the same foliation line. So on any point in the Riemann surface, there's 3 different foliations. Now, near a branch point, there's a single index which is not concerned. We're assuming that the branch points are simple. So a branch point permutes 2 of the 3 indices. There's a third index which is not concerned. So there's 2 indices which are interchanged. And the picture of the foliation concerning, for the 2 foliations, for the Rij foliation at a branch point looks like that. Now, Gaiotto-Moore-Neitzke, so this is the work which we've been interested in looking at, the work of Gaiotto-Moore-Neitzke. They've defined a subset of X called the spectral network. It starts by using the initial foliation lines coming out of the branch point. So every time we have a branch point, we have these three singular foliation lines. That's sort of the start of the spectral network. However, and we can talk about the spectral network in the case of SL2, but in the case of SL2, that only consists, in the case of SL2, there's only a single foliation given by a quadratic differential, and there's only these singular leaves of the foliation. But in the case of SL3 and higher, something new happens, which is called a collision point. This is what Gaiotto-Moore-Neitzke have actually introduced. So let me just draw a picture of a collision. Sorry, maybe I should say one thing, which is, remember, this was a point for the ij. This point was labeled ij because I and j were the two sheets of the spectral curve that were interchanged when we went around this branch point. So these guys are labeled ij. Now, if we have a line labeled ij, so that means it came from a singularity way back here. We have also a line labeled jk, which came from a singularity back here. Then they can collide and form a new line labeled ik. So this new line did not come from a singularity. It came from colliding these two guys. And these guys are physicists, so they like to collide stuff. Now something called a BPS state, which I guess stands for Bogomolny-Basad-Sommerfeld or something like that, which has to do with black holes maybe or something like that, among other things. Anyway, for us, it's just a combinatorial structure on the Riemann surface. It's what you get when you start with these singular points. You start zipping out these spectral network curves, then you allow them to collide, and then you keep doing that. And if you get back, every time two guys collide, then they create a new single line. And then it might collide with somebody else and so on. But there's always sort of a line which is being created. If that line that's being created sort of runs head on back into a singularity, it sort of stops there, then that's called a BPS state. So here I've drawn a BPS state with 3 collision points and 5s. Well, let me just skip over this about something about a BPS state could have a picture like that, but actually you can sort of shrink the hexagon and get something of the form that we were discussing. And so this is also sort of the history of spectral network. I can read that for a minute. Check my time. So spectral networks are useful for lots of things. Gaiotto-Moore-Neitzke sort of said all this stuff basically. That they're related to WKB asymptotics. They're related to Bridgel and Smith's theory. So that's why we were interested in spectral networks. This was, Ludmilla, I don't know who else here had to go. But anyway, Ludmilla and his group were interested in looking at the Bridgel and Smith construction and stability conditions. The Conceivable-Schlegelmann wall crossing is gonna, the wall crossing is when the whole thing moves around a little bit, and every time you get to a BPS state, that's gonna be when you're on a wall. So what we have sort of been looking at adding to this whole picture here is the notion of harmonic maps to building. So, and then we've noticed that, because when we started looking at, when Gaiotto-Moore-Neitzke said, okay, this is related to WKB asymptotics, then, and also when we started, this is maybe where Fabian made a crucial remark, when we started looking at Bridgel and Smith theory and saying, okay, what's happening in Bridgel and Smith theory looks very closely related to this foliation defined by the quadratic differential. From the foliation, you could get a tree, and the walls were the places where the tree acquired a BPS state. Okay, so all that theory sort of started making Ludmilla and I, who'd been interested in harmonic maps from some time ago, we started saying, oh, this looks like harmonic maps, so why don't we look at harmonic maps? It took us quite some time to understand what was going on, but so here's a presentation of what we sort of understood here. Okay. So this is what we're looking at, is harmonic maps to building. Now, what's a building? A building, so this is just very brief. A building is a space which is covered by things called apartments. An apartment is just a Euclidean space. So the apartment for SL3 is R2. But R2 should be thought of as x1, x2, x3, whose sum is equal to 0. So there's really 3 different directions in here. And inside the Euclidean R2, these 3 directions are 3 different directions separated by 60 degrees. Okay? So, if you draw a point, you draw the 6 different lines, so that's 3 different directions. separated by 60 degrees. That's kind of the picture of the local structure of what's going on in the standard apartment for SL3. The Weil group, which is the set of permutations in 1, 2, 3, acts on this and it preserves these directions. Then what we'll call an enclosure is that any sort of compact closed subset of R2 which is bounded by the lines going only in these 3 directions. I don't know if that's very well drawn here, but these lines are all supposed to fall into 3 different parallel families of lines. Okay? And a construction is anything made by gluing together all these guys along their edges. In particular, an apartment, so for construction we said compact, but an apartment is a construction. Sorry, for enclosure we said compact, but an apartment is a construction by just tiling it in any way you want. Now, we'd like to understand what it means to have a harmonic map from an open subset of X into the standard apartment, or even into just a construction or an enclosure. Now, we can take the differential of the map. So if we think of A as being the set of points like that, and remember back here we had phi1 plus phi2 plus phi3 equals 0. Okay. That means that the coordinates x1, x2, x3 on A sort of look the same, and in fact the permutation group action is kind of the same as our differential forms here. And so we'll say that H is a harmonic map associated to the spectral curve sigma if the differential is equal to this triple of real parts of phi. And that's kind of permutation invariant. Now an affine building it's a construction which is negatively curved. That's kind of the principal property. And it's covered by things called apartments. There's a bunch of axioms which I'm not going to write down. So you might be familiar with the notion of building. The first example were Brouillet's buildings associated to groups of the form SL3, SL something or other with coefficients in QP. And let me be extremely brief here, but we're interested in the same type of thing as SL3QP or SL3 of a non-Archimedean valued field, except we're actually looking at the germs of functions on R at infinity, and the valuation is the exponential growth rate. The only problem is that's not really a field. And the fact that that's not a field is why you need to introduce the notion of ultrafiltering. So this is a theory of Perot, Kleiner, Lieb, and goes back to other people too. Here's just some properties of buildings. Maybe let me just say it for a minute. So one of the properties is that any 2 points are contained in a common apartment. Then you can define the vector distance between 2 points as put them in a common apartment, then look at the vector from R2 from one point to the other. And but the coordinates there's a permutation action on the space of coordinates. So that's not a well-defined point, but if we move it into the positive Weil chamber, then it's a well-defined point. That's going to be the vector distance. So it turns out that's a well-defined thing. Then the Finsler distance is just the maximum coordinate of the vector distance. It's not the same as the Euclidean distance. So a harmonic map associated to the spectral curve is a map such that, except for a discrete set of singularities, which is going to be our set of branch points Q, for any point there's a neighborhood of that point and an apartment such that the map factors through the apartment through a harmonic map whose differential is given by this condition. So we can kind of restate our problem. Our main question is, how can we understand geometrically the harmonic maps associated to our given spectral curve using just using this differential condition? Now we get to the sort of geometry of the situation. So we have 3 foliation lines. There are some points where the 3 foliation lines could actually all 3 be tangents. We'll call that a caustic. At a caustic, the map to the building sort of folds the Riemann surface along that caustic. So maybe I'll just skip over this briefly, rapidly. You can define it. The first thing you would try to do was you could define an initial construction and a harmonic map to that construction with a factorization property. The only, well, for one thing, that depends on the choice of covering. But the main problem is that the initial construction is going to contain points of positive curvature. So, in particular, it's going to contain what we call a fourfold points, where only four sectors of 60 degrees come together. You know, all the points are kind of, I mean, the link at a point is divided into sectors of 60 degrees, right? Because the geometry of our apartment is determined by these three sets of lines. So let me just explain how a fourfold point comes about. So this, we can see that this is a picture more or less the same picture from our paper. This yellow line in the middle, that's the caustic. These two points are singular points, and these 2 points are collision points. The black lines are spectral network lines. And so let me just draw the picture. So this is a picture of the Riemann surface X, and now let me draw the picture of the map from X into the building. It's going to look like that. So this is two sheets of stuff here, there and there, like that also. So all down here, there's two sheets. Up here, this whole stuff is all squished together to the same sheet. So if we go back, it means that this central region got folded along the caustic line, folded together. But the folding stopped at these black lines, and so this part up here and this part down here are distinct. So here everything is folded together, and up here everything is distinct. Well, our initial construction is just the same picture, except where we only fold together these shaded regions. We only do the folding along the shaded regions, but you know, the global folding is a global thing. We don't know that we're supposed to fold a point here to a point here. By kind of local considerations, you can see that locally along the caustic, one can see that one has to fold neighborhood. So the initial construction, let me just go to the picture. So kind of a picture of the initial construction at a point, one of these green points is going to look like that. So we folded together the shaded stuff, but we didn't fold together the stuff here. And you can see from this picture that inside this region, there's going to be four sectors of 60 degrees, which are consecutive. That makes a positive curved point. In any map from that guy into a negatively curved building, these four sectors have to collapse. So let me just, instead of doing the text, let me just sort of click through the pictures. So here's a picture of the collapsing. So when we have four, so these are supposed to be four sectors of 60 degrees each, but you can't draw it on a flat surface. This is a positively curved point. The total angle at one of these points is only 240 degrees instead of 360. A negatively curved point would have an angle bigger than 360. But now the problem here is that one of these points with four sectors, in principle, you can fold it together in two different ways. It's like this little, the little paper toy thing. You can either fold it like that or like that. Okay? So in fact, and this is really the problem. If there was a canonical way of determining how this should be folded together, then we pretty much be done, basically. You would just say, just every time, so this is one of these fourfold points. Every time you see a fourfold point, fold it the way you're supposed to fold it, then just keep doing that, and you can see here, you would end up eventually folding together all of this stuff, and you would have the answer. So the answer is kind of this picture with that stuff folded together. That's what we call the pre-building. That's going to be the image of X inside any building is going to look like that. So now the fundamental problem in the reduction process is that we don't know at a fourfold point which way it should be folded. So we need extra data, which is what we call a scaffolding. So if you think about it, in our Riemann surface, if we take this, in this picture, this came from a piece of our Riemann surface, in which case on one of these sheets, you would look at a little open set around this line, and you would say, okay, but my condition for being a harmonic map is that this little disk maps into an apartment in the building, and that map is given by integrating these one forms. So that little disk is not supposed to be folded. So we know in this case that these edges are not supposed to be folded. Well, these edges were just obtained by gluing together some stuff, and we don't know anything about them. So from that, we can actually conclude that these edges have to be folded, because somebody has to be folded. And the fact that these guys are not folded tells you that the information you need for the scaffolding. It tells you that the scaffolding is like we're holding up, we're sort of making some rigidity in some parts of the construction. So these guys are sort of maintained open, you might say. That tells us that we're supposed to fold in one direction, but not in the other. So the scaffolding is going to be data of edges that are folded or not folded throughout the whole Riemann surface. Then the problem is, okay, now we start folding stuff. Then we have to, in the new picture, we have to sort of understand what the new scaffolding is. Because when we fold stuff together, that creates a new edge. We don't a priori know whether it's supposed to be folded or not later on. So that's kind of the stuff we're doing now. So let me just sort of draw the reduction process and maybe I'll stop. So the reduction process, to go again, to view this again, is we're going to have a parallelogram like that with a fourfold point up here, and two different parallelograms that are going to have to be folded together. And from the scaffolding, we sort of know which direction they're supposed to be folded. Then we fold them together. Then we can do something else which is interesting, which is once we fold them together, we can actually cut that piece off and throw it away. So of course we've thrown out some stuff. So to get back to the WKB information, we might have to put it back in and be careful about what's happening. But just sort of for the geometry of the situation, we can just cut that stuff off and throw it away. The nice thing about that is we're again left with a Riemann surface. Okay? The stuff that's left over here is again a surface. Whereas if we looked at this picture, this whole thing is not a surface, right? At a point here, there's three different sheets that are coming together. Okay? But the point is that, as it turns out, as we go through this process, we can just trim away systematically the stuff that we just previously folded together and just throw it out. We get a sequence of Riemann surface. So what's interesting about that is that this sequence of Riemann surface, once it converges, once we've gotten rid of all the fourfold points, it's only going to have eightfold curvature points, or flat points. And we get a new Riemann surface with a flat structure. In fact, with a geometric structure of, it's a flat structure, but model on the apartment of the building. And it has some positively curved points, some negatively curved points. In some sense, here's going to be a picture of this negatively curved point. In some sense, that negatively curved point was really a concentration of some negative curvature that was kind of, at the start, spread out along the caustic line. Then when we did the initial construction, if you think about it, we sort of discretized the curvature which is spread out along this line. We discretized it to an 8, a 4, 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 and an 8. If you total all that up, that makes a total of, an eightfold point. The 4s and the 8s cancel out, but we get an extra eightfold point. And this process basically squishes together all that stuff. At the end, we just get a single eightfold point. So now this is just a picture to finish, to explain. So the theorem is going to be that there's going to be an obstruction to this process. The obstruction to this process is the existence of BPS states in the spectral network. Those are walls in the space of everybody. Okay. So what we're going to be saying is that if there are no BPS states in the spectral network, then the theorem will be, we haven't finished the proof, but the theorem will be that in that case we can continue the reduction process. We can sort of define the scaffolding at each step and come up with a process that's, there's maybe convergence questions also, but assuming that it converges, we'll get down to a sort of a final version, which is going to be one of these flat Riemann surfaces with just these eightfold points. But let me just explain in pictures why it is that a BPS state might sort of lead to an obstruction. So suppose we squish this up together and we have two different eightfold points which happen to lie on the same foliation line, the same line in one of these in our preferred three families of lines. So the picture is going to look something like that. Then we can draw two different trapezoids on the two different pieces below. We can either glue those together or not glue them together. So in this case, you might say, if we glue them together, then the eightfold points have moved down to here, basically. Okay. So if you have a situation, and this guy from here to here is a little mini BPS state. So if you have a BPS state, then in principle, maybe not always, but in principle, you might have a situation where the result of the reduction process is not well determined. And so the vague idea is that's what I was talking about birational geometry. Maybe along the walls, or maybe in some higher codimensions piece of the stratification given by the walls, there may be some flips and flops occurring in what's happening with this reduction process. Anyway, so I was going to describe the application, but we don't know how to do that anyway, so we just stop here.
Questions?
Well, you say a couple of words about the stability conditions application.
Okay, well, come on. Well, so the main point is it's this idea that when we do a folding together, we can then trim it away, and so we get a sequence of two manifolds that sort of reduce in size. And if you think about it, this stuff was some piece of the original two manifold, but then out of that piece we've cut out some stuff and then glued the edges together. So maybe if we go back to the original picture, this is kind of pretty much the only picture I really fully understand. Here we would cut out this whole middle diamond-shaped region, just throw it away, and glue, this edge gets glued to this edge, and this edge gets glued to this edge. And what's left over is our what we might call the core. That's actually related to something called the Stallings theory of chord graphs. It seems to be sort of a two-dimensional version of Stallings chord graphs. So anyway, so we can have this process of reducing our Riemann surface to a Riemann surface where there's this flat structure. And if you think about it a little bit, that has a new complex structure. So we're really sort of modifying the complex structure on the Riemann surface. It has a new complex structure. It has some conical points with 480-degree angle at the conical points. But also this new Riemann surface has a canonical sort of spectral curve over it, which are the three different differentials. But now it's a cyclic spectral curve. Now the spectral curve is a cyclic covering. So it turns out that in terms of spectral curve, that's the spectral curve given by just a 3 differential. Generally speaking, for the equation of the spectral curve for SL3, there's going to be a quadratic differential and a cubic differential. But this guy is a spectral curve given only by a cubic differential. So the basic idea is that we would then like to say, okay, we have this way of reducing to spectral curve with a cubic differential. We get this core. The only thing is that core might depend on the direction that we started. So if we replace phi by e to the I theta times phi, the core will be different. So for each different phase, we'll have a different core. Now the project we're currently trying to work on, and I think here Fabian is also participating. The project we're currently trying to work on is to define the stability conditions in the case of a cubic differential. If we can, so then the theory of how this might apply to get a generalization of Birch-Smith is, suppose we can define a stability condition for a cubic differential, then we get a stability condition for each one of these core guys. Then we could try to define the category of objects of phase less than or equal to theta by taking the core at that phase theta, maybe there should be a minus sign here or something, taking the core at that phase theta, using the stability condition that we would know by the cubic differential, to define the d less than or equal to theta, and then sort of just combine those guys together for different values of theta to create a stability condition in general. So it's not going to be a stability condition associated to a cubic differential. It's going to be sort of a stability condition where each one of the hearts, or these are a bunch of different hearts of T structures. Each one of the hearts is going to sort of be the heart of a stability condition for a cubic differential. But that Riemann surface with cubic differential is going to sort of be changing as we change theta. So that's a very quickly the idea.
Any other question? Okay, so let's thank our speaker again.